All right, so I wanted to go over this concept called polar molecules. All right, polar molecules are also called dipoles. All right, so sometimes you'll hear it called polar molecule, sometimes you'll hear it called a dipole versus a polar bond. All right, and we've already talked about polar bonds, and there's also what's called a polar molecule. So what's the difference? All right, so take a look at this molecule right here. All right, there's only one bond in this molecule, and you should be able to figure out that this end right here would be delta negative, this end would be delta positive. That's because the chlorine is more electronegative. What that means is that electrons are being pulled more towards the chlorine. All right, so this is a polar bond. All right, but if you take a look at this molecule, think of it as being a molecule as a whole and ask yourself, would there be a more positive end of this molecule and a negative end, or a positive side and a negative side? And hopefully you'd realize that overall this end right here would be more negative than this end right here. All right, and that's a pretty simple example where the overall molecule is polar. It's got a partial negative and a partial positive side because it's got a polar bond. All right, so here are two quick rules for you. You can pause the video and write these down if you want to. But essentially, if all the bonds in a molecule are nonpolar, then overall the molecule is nonpolar. All right? If a molecule contains polar bonds, it might or might not be a polar molecule. All right? So it would be nice. It would be pretty easy if you just say that if it's got a polar bond, it makes a polar molecule, but it's not quite that easy. All right? So first of all, why is that the case? All right, we'll take a look at these two molecules right here. All right, in this example right here, if we look for polar bonds, okay, carbon, hydrogen, that's not polar. Carbon, oxygen, okay, that's a polar bond. All right, we know that the electrons are going to get pulled towards the oxygen. Okay, so what we're going to do is we're going to compare that to this right here. Carbon dioxide. All right, we know that the electrons are being pulled this way in this bond. We know that they're going to be pulled this way in this bond right here. All right, so here's the thing. Would this right here have a positive and a negative side? All right, well, if the electrons are being pulled in this direction right here, first of all, we know that the shape of this molecule is trigonal planar. All right, and you have to ask yourself, if the electrons are being pulled this way, would this molecule overall have a positive and negative side? Yeah, all right. This top half would be sort of negative, and this bottom half would be sort of positive, and it happens because of this polar bond right here. All right, electrons are being pulled in the upwards direction. All right, but let's take a look at this molecule right here. This is a linear molecule, all right? The shape of this molecule would be a straight line based on VSEPR theory, all right? And this thing is being pulled that way, this bond is being pulled that way, all right? This is a nonpolar molecule even though it contains polar bonds, all right? So why is that? Well, let's just think about this. Would there be an overall positive side versus a negative side, all right? Here, you're essentially having the electrons being pulled equally but in opposite directions, okay? And so this is a linear molecule. It contains polar bonds, but because they're being pulled in exactly opposite directions, the overall molecule is considered nonpolar, all right? So a way to figure out whether something would be nonpolar versus polar is to think about it this way. If I were to grab these oxygens right here and I would pull them in the directions that these arrows are showing me, would that central atom move? All right? If I pulled both of these in exactly the direction that they would occur, because this is linear, remember, that carbon would stay exactly where it is. All right? It would be a tug of war between equals. All right? So let's take a look at a couple of other examples. All right? Let's take a look at this molecule here, for example. All right, so All right, so taking a look at this molecule here, first of all, we've got to figure out what shape it would be. This would be tetrahedral. All right, so it's going to be this shape right here. All right, so within this bond, or sorry, within this molecule, are there any polar bonds? All right, all of these are carbon-hydrogen bonds. They are all nonpolar. Okay, so since the molecule is going to be considered nonpolar, all right, so let's do something a little different. Let's pretend that we had this molecule right here. All right, so again, the shape of it, it's going to be a 4-0, which makes it tetrahedral. And so it would be kind of like this right here. All right. So are there any polar bonds? All right. Yeah. Electrons would be being pulled towards that fluorine away from that carbon. Okay. And so what you have to ask yourself is, would there be a way to say that one side of this molecule is more polar, or sorry, more negative than the other? All right. Take a look at the way it is right here. Does it make sense that the things on the back side of my hand would be more negative than on the palm side of my hand? All right. So because this side of the molecule is more negative than this side over here, this would be, we would say, yes, this does have a polar bond, and therefore it is a polar molecule because electrons are pulled to one side. Okay, and so here's a way to figure out whether the molecule is polar or not. All right, picture taking this molecule, this model, and actually pulling on the atom in the direction that the arrow would show. All right, so the arrow shows pull towards the fluorine. If I were to actually pull this thing in that direction, pull it up, would that central atom move? All right, if it moves, then it means it would be a polar molecule. All right, so let's do another example right here. Let's say that we were doing this right here. That would be this molecule right here. And so again, electrons are being pulled towards the fluorines. All right, and so ask yourself, if I were to take this and pull, if I pulled this atom in that direction and I pulled this atom in the direction that it is, right, would it get pulled in a direction? All right, if I hold it like this, hopefully you'd see that this side, the back side of my hand, would be relatively more negative than the palm side. All right, this is the negative side. This would be the positive side over here. So this right here is a polar molecule. Okay, so just one last molecule. Take a look at this one right here. You've got 4 polar bonds. Each of these carbon-fluorine bonds is polar. So the question is, would that make a polar molecule? All right, well, take a look at the model. All right, this would give a tetrahedral shape since it's 4-0. All right, it does have polar bonds, but if you think about this, if you were to pull the electrons in the directions of the arrows, imagine like pulling equally on all 4 of these green balls here. Would that ball get pulled in any direction? All right, because all of the directions that the electrons are getting pulled would cancel each other out, this would be considered a non-polar molecule because electrons, it's not because the electrons aren't getting pulled, but they're being pulled equally in all directions. Okay, so just to sum up, if you want to figure out whether the molecule is polar, first draw the Lewis structure. All right, based on the Lewis structure, determine the shape of the molecule. then determine which ways, if any, the electrons are being pulled. For example, for this molecule here, you would need to realize, okay, the electrons are being pulled equally around that tetrahedron, and then determine whether all of that pulling would cause either a positive side or a negative side of the molecule.